All right, hi everyone. Thank you for coming. My name is Wesley Yu.
I'm Kiva Villegas.
This was our undergraduate research project at UC Austin. So what we're going to talk about today is a low mass, low cost EDL approach to a manned Mars mission. And while we will focus on the EDL portion mostly, we did also kind of consider the habitat designs and how it relates to the mass limitations of the EDL process, as well as the radiation mitigation throughout the entire duration of the mission for the astronauts. And so before we started anything, we wanted sort of like a reference and comparison for our project. And obviously we started looking, and the first one that popped up was the NASA DRA 5.0. Had a lot of good information for us to kind of reference and compare. And then more recently, the SpaceX Interplanetary Transport System, the ITS, was a much more ambitious project, much more ambitious approach. They're trying to land a lot of mass at once, and we'll see how they're going to go about that in a little bit. And then our mission architecture is a little closer to NASA's approach, however, with a lot of modification in our EDL process. And so I'll go into that in a little bit. And so while all three of these projects have vastly different architectures, I think it's worth noting the similarities before we go into anything. And so the first is that the cargo is sent to Mars before anything else, usually 2 years before. This is just to make sure the astronauts have a safe environment to arrive in. We know everything works before we send the astronauts. There's also an interplanetary transit habitat for all the crew. We have to keep them alive. That's kind of a big deal. And then also, finally, the dependence on upcoming heavy lift launch vehicles. So this would be the SLS, the future versions of the SLS, as well as the ITS. And so when we first started looking at possible architectures, this is NASA's kind of blueprint for that. They had an initial cargo launches 2 years before, sending the habitats, ISRU equipment, let's see what else, the ascent, descent vehicles for the astronauts on the surface. And then 2 years later, sending the components for the transit vehicle, assembling in low Earth orbit, and then attaching the Irvine capsule for the crew. They'll stay on the surface for about 600 days, gives them a lot of opportunity for science and expeditions. However, this does incur a lot of mass in the entire mission. That was kind of a sticking point for us when we were trying to design our mission. So while they're sticking around for 600 days, we are opting for a much shorter stay of around 40 days. And on their way back, very conventional methods, landing in the ocean. And so just to get more of the basics out of the way, we've got the heavy lift launch vehicles. ITS obviously is a much higher projected landed mass of 330 tons. They're going to land that entire top payload as one single capsule. So it's going to be a pretty advanced propulsion system. And then SLS is a significant step down. But then the Falcon Heavy we considered for some of our approaches, but we're probably not going to use any of it for the purpose of our mission. And then finally, the transit vehicles. SpaceX has its spaceship that it'll land all at once vertically on the surface of Mars. And then NASA's transit vehicle, which again, we are kind of more similar to. They've got the Orion capsule in front, an inflatable habitat, and all the science equipment, fuel tanks, and everything. So what we'll focus on is kind of modifying the front of our mission. We will have a more modular approach to everything. So common problems for mission designs for Mars, first being limiting the astronauts' radiation exposure. Obviously, this can cause significant health effects. It can hinder their ability to perform on the mission and also cause death in the worst case scenario. So it's not a problem we can just ignore. I know some astronauts might just say, forget about it, I'll go, but I don't think that is a high priority for us. And then also the EDL process. This comes into play during the crew landing vehicle descent, as well as the Martian habitat design. The Martian habitats that are currently proposed are very high mass, a single habitat that can be very hard to land, that we haven't been able to do in the past. And so this kind of stems into the problem of what we saw in EDL. As I was saying, the largest mass we've successfully landed on Mars is entry mass of 3 tons, which is the Curiosity rover in MSL. That's the best we've done. and SpaceX wants to land 330 tons, and NASA wants to project 20 to 70. So that's a huge jump, huge order of magnitude difference. And and as we started our project, we kind of looked at, okay, so how do we want to approach our mission architecture? With larger entry packages, with smaller entry packages, what we defined as that was greater than 5 tons would be a larger entry mass, and then smaller entry masses would be less than 5 tons. So with larger entry masses, you're going to need much more sophisticated technology, namely the propulsion system, also the aerodynamic system, because of the density of Mars' atmosphere, which is about 1% of Earth's. It's enough to cause a problem, not enough to slow us down effectively. So we need a lot more research and development in propulsion and how to slow us down. And also, we might not be able to launch our EDL system with the crew simultaneously, and that also adds complexity to our system. So when we started looking at smaller entry masses, what we found was we can just do everything on our mission with current technology, which is kind of a theme of, I guess, these few presentations lately. We can do it with everything we know currently, and that brings down the cost of research and development and also the time that it takes to take on this mission. The downside, however, is you're landing many more times on the Martian surface. You're also sending a lot more missions in total, which gives it a lot more room to go wrong. Your sample size increases. And so that is a downside to that. So, and then we wanted to start doing comparisons of EDL processes, and we didn't want to just do hand-wavy stuff and say, oh, this is better, and blah, blah, blah. So we went with the traditional Mars entry process, which is a hypersonic entry with parachute deployment at 11 kilometers, and then a final leg of propulsive descent, which is based on MSL. And to model the path and velocity of the spacecraft, all we had to do was model the hypersonic regime of the reentry using a system of differential equations based on the equations of motion with a Mars-centered reference frame. And here are the 3 kinematic relations that we used for this. And this gives us a profile of the velocity and position of our entry vehicle. From that, we can also calculate the thermal loading, max thermal loading, and the thermal profile of our entry vehicle throughout the reentry process, and that gives us the mass we need for the thermal coating, I guess. And so this will give us a relationship between the entry mass and landed mass, which is the main thing that we needed. So for MSL, the entry mass you can see right here with that red dot, that's MSL. And so we use that as a reference point, and then using those equations, we were able to iterate through and just find a relationship between entry mass and landed mass. And as you can see, our curve lines up pretty well with what we predicted for MSL. But once we get to 3.5 tons, as you can see, the linear relation stops, and we get an exponential jump in entry mass. And so we said that our limit for current technology using MSL specs and everything was about 3.5 tons that we could land on Mars. And so obviously there's this limit right here that we can't go past. And just again, as a reminder, NASA wanted about 20 to 70 tons for its habitat landing, and SpaceX wants 330 tons. So where are we going to cover that gap? This was a couple years ago, and we're like, what are we going to do? So we tried initially to maybe start stretching the envelope of what we could do with EDL. We ran the same code, same MATLAB code, and just added Raptor engines, changed the shape of our entry vehicle. Instead of using our traditional capsule, we tried a lifting body, and we were able to stretch it out to 35 tons of landed mass. It's an improvement. We've gotten inside the range of NASA's requirement. However, it's still a far cry from SpaceX's projection. And so that was our main sticking point, and we kind of hit a roadblock here and said, okay, we might have to rethink how we're going to approach this. We wanted to focus on current technology and keeping it low cost, so we can't just come up with some crazy new idea for this. And so, again, just trying to recap, that's the difference in our capabilities of mass landed. So now Kiva is going to talk about how we went about solving this problem.
So what we propose is breaking the large smaller pods. For the manned missions, these are like actual pods, and then for the habitats, we propose sending little modules that would come together into a grander habitat. And this is again proven astronauts total on the surface, and one would stay up in orbit just in case kind of a scenario. And each entry pod has a 2.5 entry mass and 1.6 landing mass. So here's a really rough depiction of what a transit vehicle configuration could look like. The light pods attached around the Orion capsule. And we have 3, an extra one just for redundancy. Another really rough model of what the rover pod docking would look like. So for our pods, in order to cut down mass, we wanted everything to be automated, including the rover. So what we have is the pod to land, and then what we kind of consider a cookie sheet method would occur, where a conveyor belt would pull the astronauts into the rover, which would be automated and would take them to the habitat modules, which would also have a cookie sheet kind of method pulling them into the habitat. So there's some pros and cons to this. Obviously, we've reduced mass a lot. We offer contingency plans, not only just separating the astronauts, but also having a third pod just in case. And again, we sent them a week apart so that the first set of astronauts have time to acclimatize to the Martian environment before the second set comes, and they're ready and prepared to do so. And any last minute things that need to happen to the habitat can be done before the next set comes down. The cons to this is that we're asking for a lot of moving parts. Everything is automated, and there's multiple parts, so I mean, there's a lot of chances for something to go wrong. In terms of the habitat considerations, in terms of what it's made out of, we considered radiation mitigation as kind of like our basis. So for our habitat modules, we're using aluminum cylinders with a Vectran dome on top, just to increase volume. And then for the volume requirements, we used NASA's Human Integration Design Handbook, which gave us this equation for the net habitable volume for each crew member based on the duration of the mission. They also have an equation for pressurized volume based off of the net habitable volume, and that's how we determine the overall volume necessary for a mission on the surface, and again, the transit vehicle also. But then how to break up this volume into each individual habitat module also had to come into play. So the launch vehicle payload bearings really kind of decreased the size of each habitat module. We ended up determining a 2-meter radius cylinder would work, and we have 4 of them. And then another member of our group developed a MATLAB code that would take the number of astronauts, straight time, volume requirements, some other things to figure out how much space and mass would be necessary for each leg of the mission. So again, we have 4 mobile units that would come together into one habitat. We figured out that you could send 2 per SLS Lunch. These would come together and also dock with the rover. And I did say mobile. They are on wheels. This is a mistake. Because of the way landing these would be, since we're not landing it all at once, you can't land the things right on top of each other, and it needs to be prepared before the astronauts get to the surface. So they would have to come together at some point. The wheels would be necessary. Now, taking a step back, I want to talk about radiation. So just some background on radiation effects on astronauts. There's 2 different types, solar particle events and galactic cosmic radiation. Solar particle events are obviously coming from the sun, which is one directional. Galactic cosmic radiation is coming from all over the universe, so it's omnidirectional. You'd have to shield basically everywhere. Solar particle events are mainly made up of protons, which are lighter particles. I mean, they still do harm, but it's not as bad. Galactic cosmic radiation is made up of lighter particles and heavier particles such as iron. This poses a greater risk because when iron hits cells, it can decompose DNA, which cannot be reversed, and this is largely shown in cancerous effects. Just some more reasons why radiation matters. GCR is more of a long-term risk. So over the course of a year, a 0.4 sievert radiation dose increases cancer risk. 2 to 4 sieverts causes radiation syndrome, which has clinical effects that you can see. I mean, it's not regular. But solar particle events are more like acute radiation doses. You can get them They largely last somewhere between a couple hours, maybe at most a day, but the dosages can be much higher, and it's all at once. So here's some effects. Using NASA's online tool for the assessment of radiation in space for PARES, we were able to determine how much radiation an astronaut would receive based on different types of shielding and different shielding thicknesses. And so using that and just putting in a baseline thickness for the normal type of spaceship without any shielding, the radiation dose that they could receive, the maximum radiation dose is 2.25 sieverts, which is very close to causing death over the course of months. So obviously shielding is required. You can't just not shield. NASA imposes an overall career limit to how much radiation astronauts can receive, and this is corresponded to a 3% increase in the risk of cancer. Depending on age and gender of the astronauts, this can be somewhere between 1 and 4 sieverts. So considering that the crew is going to be made up of multiple people, we decided to implement a 1 sievert limit radiation dose, just in cases. So there's 2 different ways you can mitigate, really, like it comes down to either putting shielding or decreasing mission duration. So we decided to do a bit of both. We said our Mars surface stay will be 40 days, and then we really wanted to add shielding. But the problem with that is, considering the volume that would be necessary for a transit vehicle, shielding the entire transit vehicle somewhere between even just 5 to 10 grams per centimeter squared of polyethylene is equivalent to somewhere between 17 and 31 tons of material, which is just not feasible. Getting it into space or just assembling it would require just too much. So we considered shielding just a smaller area of the spaceship, kind of considered like a shelter for a radiation storm. And how we broke down that mass is we broke down the hours spent each day doing crew activities, and we said that if the meals, sleep time, and free time were all spent in the same area, this corresponds to about 13.5 hours a day of usage during weekdays and 19.25 hours during weekends. And if you just shielded that one area, the radiation dose would be enough would be within that 1 sievert limit. And we considered using different materials, obviously the waste, because there's going to be some water, polyethylene. And we decided to use water and polyethylene. We calculated how much water would be necessary for the duration of the mission, and then decided to use that as the shielding. So for our duration, for 5 crew members, it ended up coming out to be a 14.83 grams per centimeter thick shield of water, and we included an additional 5 grams per centimeter squared of polyethylene shielding for just this one compartment. And we decided not to use aluminum, A, because it's very heavy, so the mass is just a lot more, but then also when you take into account that thickness matters and how much shielding you use, there comes a point where it actually does more harm than good, just because of the way second scattering happens when it collides with the iron particles. Those do a lot more ill harm to a human than just if it had just hit straight without any shielding. And in terms of thickness of shielding, it hits an exponential point where it just doesn't do any good at a certain point, which is around 20 grams per centimeter squared. So you can't really go beyond that thickness. Anything after that doesn't really help. So we did choose water and polyethylene. We also considered that we can predict a solar flare with enough time that should one happen while the mission is going on, they have enough time to get into this sort of sheltered area. So that considered the maximum acute dose that they could get during a solar flare if they are inside this shielded area is 0.11 sieverts of radiation, which has basically no effect on the astronaut. Like I mentioned earlier, we broke it down so that 2 astronauts would go to the surface. A week later, 2 astronauts would stay, and then 1 would stay in orbit the entire time. But even considering that each of those astronauts is going to have a different dosage, none of them will receive a total mission exposure dose of more than 0.95 sieverts. And since the water is going to be what is already necessary for the mission, we didn't consider it an added mass. It's the only added shielding is the polyethylene, and that adds 1.7 tons to the overall transit mass, which we deemed acceptable considering the trade-off. So, just like a summary of what we talked about today, we proposed pods for the entry of the human part of the crew mission, and then for habitat design, modules. And this is all based off of what has already been sent to Mars, so it can work. And then in terms of radiation mitigation, we want to use water and polyethylene and concentrate it around a fixed area to conserve mass. Acknowledgements, our academic advisors, Drs. Hansmark and Humboldt-Vandell, and all the other undergraduates who work on this book. Any questions?
What about the burying? In other words, using Martian soil, rock, or material to bury part of the housing as a radiation?
So in terms of like the radiation dose, because we're going for 40 days, and technically half of the exposure is like covered because of just the surface of Mars. So anything coming from that half is not there. The radiation dose by itself, even without shielding, is very low. The atmosphere also helps to prevent anything from solar particle events. But we consider just like what the base structure would be made out of. And then in terms of like digging, that might be more feasible for a long duration, but for 40 days, just the cost of doing that and how much effort would be required, which just wasn't worth it. The radiation is again very small, just based off of what the
So the problem there is the digging.
yeah.
If you can solve the digging problem, then it might be a more doable option.
You know, for the long-term transit part, people looked at like localized sensitivities to radiation in the body. So maybe you're shielding the whole body, but obviously there are organs like the thyroids and all that are much more sensitive to cancer. And whether your fingers would get cancer for high radiation dose versus your organs. So is there ways to do, let's say, you know, torso type?
That model actually breaks it down into like every part of the body. And so it's kind of like the overall, all those numbers I listed were the overall radiation dose a person would receive. But it also breaks it down into individual parts because, of course, there are some areas of the body that are a little more susceptible. Anyone?
This might be a stupid question, but is it possible to use an airplane? How long a landing strip would you need in that atmosphere? That traffic?
Well, we haven't looked at it.
We kind of thought about like using the water way at the beginning, but then I think we just decided that the atmosphere is just too thin.
In order to have an airplane that can effectively carry the mass, I think, in the Martian atmosphere, you need an extremely high aspect ratio. So we haven't looked into like specifics. I think we crossed that off.
We crossed that off a
long time ago.
We looked at it.
We did look into possible probes, I guess, for using drones with high aspect ratios, but that was also side that we never thought of before.
What about some of the earlier concepts from decades ago, owl wings and even very large-scale controlled parachutes?
We did consider this.
I think what we were kind of, we looked at that and then we wanted to focus on current really readily available technology.
Part of it was also just the fact that the effects of being in space for all that time on the astronauts were already going to be very weak, and we weren't entirely certain they could handle the loads of doing just straight versions.
Yeah, I like the pods to decrease the land mass. Just one concern I have is dispersion, dispersion of where the pods might land if they're too far apart.
Well,
it's kind of a bad thing.
Well, I think actually one of the former professors at UT, he worked on like control systems for Curiosity. He's able to kind of guide the landed package to about 1 meter accuracy, and so we have kind of like a general landing site. When we pick out a landing site or a flat area, and we now have the capability of kind of assigning a location for moving landing. Given, I guess, that's if things go right, obviously if things go wrong, and so that could be an issue, but that's why we have the automated systems there set in place beforehand to kind of deal with that. But that definitely is a consideration we need to look into when considering this, because we did say with more moving parts, the chances of something going wrong.
And I'm hearing this thing about cheat, you know, everybody knows something is cheap, but, you know, safety is very paramount, especially in this venture that we're trying to go on to. And so ideally, I would think, you know, how much shielding, especially when we're doing radiation in different directions, or our travel through Mars, is really needed. And let's not talk about, you know, the cheap side of it, but I mean, ideally to have a successful venture in this process of mankind that is really needed. I mean, this is ideally where, I mean, how much you would think, you know, cost per, you know, tons of the CH4, poly, yeah.
So again, the biggest, again, they're getting like a lot of cosmic radiation and even the solar wind over the course of the mission. The biggest thing is the solar flares. Those are like really large doses all at once. As long as they have a shelter and can get to it in time, it's fine. I was just reading a paper this morning that said they can predict solar flares within a couple days accuracy just looking at the magnetic fields of the sun. So obviously with that, there's enough time for them to plan to spend.
But there's a certain timetable where Mars and Earth are close together that we need to launch this out. So it's, you know,
Yeah, it's like once every 19 months is like the optimal time for
how many launches can we do at that time?
I think, I know NASA's plan is like at least four launches, I think of an SLS in each window.
So you think we need more launch pads?
Pretty close to
I'm sorry.